We're learning something called trapezoidal rule today, right? And with trapezoidal rule, it's actually in your textbook. It's actually one of the first things that you look at when we look at integration. But I've skipped and I've come back to it for a reason, right? So the trapezoidal rule is basically an approximation to finding integrals, okay? So why would we want to do that? Let's take something like this, for example, right? If I take 3x squared, and I'm integrating this, let's choose some bounds. Let's go from 1 to 4. Angus, how would I integrate this guy? Yeah. So that would become x cubed, and then 3 divided by 3. That would just divide through, so we don't need to worry about that, right? And then I'm going from 4 to 1. And then I'd evaluate it, right? So I'd get 4 cubed minus 1 cubed. And do you want to check that in for me? 64, okay? 63? 63, yeah. Okay. Now, what does this number represent? Right, it represents two things. First of all, it represents whatever the integral is. That's like an operation we do, right? But we also found another like surprising result. And it was that if I sketched out this curve, it's a parabola, and if I went from the bounds 1 to 4, it gave me the area underneath that curve, right? And that's a pretty surprising result that these two things are related, okay? The trapezoidal rule basically does the opposite of that, right? It's saying, okay, from this area, I'm gonna try and find that area, and I'm gonna get an approximation for this integral. So what the trapezoidal rule will do, will say, hang on, this situation over here, right? Instead of actually using this new technique that I've learned of integration, I'm actually going to try and think about, hey, how could I find the area underneath this curve? Or how can I try and approximate it, right? If you think back to when we started looking at areas under the curves, we tried to use rectangles, and we found that very quickly they weren't very accurate in terms of the area that they represent. What's a better shape that we can use? Well, they provide us with one. They're saying, hey, use a trapezium, right? This is what the trapezoidal rule is saying. And if you can use a trapezium to try and approximate the area, that way you can actually see what this integral might be. So where would you construct the trapezium? Well, the idea is you construct it like this. So something like this, I suppose. So you can already see it's not going to be entirely accurate, but let's go along with it and see what the estimate would be, right? I can see I've got a trapezium here. What's the form of a trapezium again? Does anyone remember? No, that's right. It's one of those ones where you're like, oh, I'll never need that, except when it comes back up again in advance, right? The formula is the area is equal to, there's a few different ways to write it. One of the common ways is h on 2 a plus b, okay? H on 2 a plus b. So what's h? H is the height of the trapezium. So usually you think about height as in like vertical distances, but then here, just be careful, right? The height is actually this length over here, because we're looking at the height of a trapezium, and then these two side lengths, they're parallel, okay? So those are going to be your A and B. A and B are the two parallel sides. Those are the two sides. Okay? So let's go ahead and try and see what this area would be. Yeah. The idea is we can go from, okay, I want to find the area under this curve, and that's going to be the same as evaluating or approximating the integral. Does that kind of make sense? Right? So let's go ahead and find the area here, right? What would the area be? The area would be of this trapezium, right? It would be half, or h on 2. So what's your h value? Now remember, it's the difference between these two, right? So just be careful. What's the difference between these? -3. Well, 1 minus 4 would be -3. Yeah, for 4 minus, we just want a positive value there, so that'd just be 3, right? So 3 on 2. And a plus b, how can I work out what my a and b lengths are? What? Good, yeah, because substitute back in the equation, because these are just y values, right? These are going to be the y values for this expression here. This is y equals to 3x squared. And if you put your x value into, you're going to get a height, which is going to tell you these lengths here, right? So this one here, that would just be 3 times 1 squared. That's just going to be 3. And this is a bigger number. That's just 3 times 4 squared. Okay? And you go ahead and put that in your calculator and see what we get. 76.5. How close would you say that that is to what we were meant to get? Not very close, right? So you may be wondering at this point, hey, what's the point of learning about this if I already know a way to find the exact area underneath the curve? I'm using like some sort of inferior way, right? I'll explain to you why. Because this is kind of a perfect scenario where you have the expression to integrate, right? This one, all you need to know are just some distances. And so commonly what they'll do is, if you want to find the area of something that's a bit of a strange shape, we can actually use this. We can break something down into various other shapes. What have I got here? I've got a drone, and what does it look like it's doing? Yeah, right. So they commonly use drones for like agriculture and stuff now to try and find areas of, large plots of lands and things like that. And pieces of land aren't always just like rectangles and things. There's like curves and different boundaries going on. So this is an example of how a drone might try and map out how much area a land has. Here's another example. Here's like a field. And you see they've kind of separated into these shapes here that we can use to try and find the area of what this is going to be. So that's the idea behind trapezoidal, right? It's more of an applied situation because you may not know if there's a curve here. You can't just say, oh, I know what that looks like. That's like y equals to x cubed plus x squared, right? Like you wouldn't know that. So in this kind of situation, that's where trapezoidal rule becomes more relevant, right? So the idea is I'm going to be able to use this method to try and evaluate and approximate integrals. Let me give you another one to look at, right? So let's take this one. So we already established that this is not really accurate, right? Can you just have a think for me and think, how did we start making our areas more accurate when we were looking at like the integrals? Like remember how we looked at like using all these rectangles? How did we start to make that more accurate? Because we started off with one rectangle, right? And we saw that it wasn't very good.
Use more rectangles.
Yeah, the more rectangles you use, like the more accurate it's going to get because it's going to start closely matching the curve more. And that's exactly what we can do here with these trapeziums. What they'll do is they'll start saying, okay, this is kind of one application of this trapezoidal rule. Because all we're doing is finding one trapezium. If I wanted to do two applications, it might be more accurate. Another way that we call this, and they commonly use, they call it subintervals. So this is using one subinterval, right? So if I want to use two subintervals, for example, it's dividing it up into two trapeziums, right? So just to get a visual sense of what's going on here, let's just draw this out again. Y equals to x cubed will look like this, right? And I'm thinking, okay, I want two subintervals. But the idea is that when I'm splitting these up, I still want them to be equal distances, right? So this is from 0 to 2. And I want to split this up into two trapeziums. The idea is I'll split it in half here, okay? And that's where I'm going to create my second one. So here are my trapeziums at the moment. Right. Let's think about this first trapezium that we see. Like what's the length of that first side? Well, there's nothing there, so it's just 0, right? So nothing too interesting. What's the length of this one? Well, that's just, we have to check in our function values again, right? So this is y equals to x cubed, right? And so always want to be thinking about your area formula for a trapezium, right? So h on 2, a plus b. The good thing about splitting up evenly is that your h value is just equal now, right? So it's just 1 in this case. So I've got here 1 on 2 outside of 0 plus, well, let's just go if I put in x equals to 1 here, I'm going to get y equals just 1 here. And then this part over here, well, let's check this trapezium that I've created over here now. I already know that that height there is 1 because I've used it here before. What about this one over here? What would this going to be? His height. 8, yeah, because if you put in 2 cubed into here, so x equals to 2, y would equal to 8, that whole height would be 8. And so we'll get something that looks like this. Right? And when you put that in, you should get 5, I think. So again, the idea is, okay, this is meant to be an approximation rather than actually working out what this is exactly going to be. We have methods for that, we have integration for that, right?